Finding the main stress and deformations of the elastic element. This article number 7.6 of the book Mechanical Systems Calculations of the Marine Facilities. Let's consider the exercise. We did consider this exercise just for the partial calculations we did in the article number 7.3, as I remember about that. The exercise, the data we have, the normal stresses and the tangent on one acting on the elastic element. On the shown on the figure 7.6.1a are assigned sigma y equal to 10 megapascal is sigma y. This is flat stress state, so we have, assume that we have two axes, ordinate axis y and the applicate axis z, and as well we assume that as well we have the longitudinal axis x, but it directed towards the plane of the considered issue. But we consider the flat stress state, and besides of the in the flat state, besides of two normal stresses and one tangential stress, we assume that we have as well the normal stress directed to the longitudinal direction, to the directed parallel to the abscissa axis, which is not which is out of the plane of the consideration of the flat stress state. So in the flat state, we have two normal stresses, sigma y 10 megapascal and sigma z 14 megapascal. We have tangent stress minus 50 megapascal if we direct downward, but the tangent stress is this is magnitude. It's minus, means that the tangent stress directed downward on this definite one side of the segment of the mechanical body, and due to the law of the pairing of tangent stresses, we have just only tau within no indexes. So this tau is equal to this one tau. So we have to find the main stress is directed perpendicular to the main normal stress is directed perpendicular to the sides of the segment of the mechanical body, in which the tangential stresses will be equal to 0. Have to find the maximal tangential stress and the magnitudes of this main stresses, and we have to find as well the main deformations in the directions of the application of main normal stresses. And we must to check the strengths of the this definite one segment in the definite point of the stress strain state. By the criterions we had of the strengths and the normal permissible stress equal to 100 megapascal, Poisson ratio 0.28, and the modulus of the elasticity 2.1 multiplied by 10 power to 5 megapascal. So first of all, let's a little bit repeat that the calculation which we did in the previous one of the previous articles. And the article, as I remember, 7.3. This was the, just repeat, how did we find the main stresses? Main stresses sigma 1, sigma 3 applied perpendicular to the sides of the segment mechanical system, in which the tangential stress equal to 0. And what is the angle of the inclination of this definite one segment sides to the assigned axes y and z for the flat stress state. So first about the angle of the inclination and the main normal stress and the maximal tangential stress. So the rotation angle of the sides with the main sides is determined as, so we had the formula in the article 7.3, tangent of two alphas of the maximal magnitude of normal stresses, we can find just due to the assigned magnitude tangential stress and the two normal stresses assigned. And after the substitute, we have the tangent equal to minus 3.333, etc. So that's why the alpha, two alphas, angle of the inclination of the main sides equal to minus 73.30 degrees. That is just only one alpha is equal to 26 minus 26.65 degrees, approximately minus 37 degrees. So we can indicate the main direction of the application of the main stresses. Main normal stresses sigma 1, we have to just rotate the axis of the application of the main stresses normal to the angle of alpha 37 degrees. And the direction here can be found in the direction of the application of the tangential stress. This minus no mean the magnitude of the tau. This minus mean the direction of the tangential stress is applied to this definite one side, definite one phase of the segment of the mechanical system. This tangential stress directed downward. Due to this one, we can find directions of other taus. Taus applied to other sides of the segment of the mechanical system. Okay, so next, let's consider the main stresses. The main stresses we can find by the good formula is sigma, or maybe 1 or 3, because we have plus minus. The first summand is the ratio of sigma y plus sigma z divided by 2, and plus just a half of square root of total. In the brackets we have the normal stresses sigma z minus sigma y. It's not so much important what direction which one is minus and which one subtracting, due to we have the square degree. So this is positive result, and plus 4 multiplied by tau squared. So we have that the main normal stresses is 25 plus minus 52.2. So 1 at least is, we use if a plus, that is 77.2. If we have minus, we have minus 27.2. And now we see that the second one, normal stress, is the number 3, because the number 2 is the stress directed in the parallel to the abscissa axis x, directed to the right, as because we assume that for this flat stress state, the stresses in the direction applied in the direction parallel to direction perpendicular to the plane of the consideration of the flat shore, this stress is normal will be equal to 0. That's why E0 is the magnitude. But in the intermediate between 77.2 and minus 27.2, in the intermediate we have 0. 0 is the sigma 2. Sigma 2 in the direction of the axis, abscissa, indefinite assigned exercise, in which we assume that in direction of the axis, let me repeat, the normal stress equal to 0 due to the assignment of the flat stress state. So now it's very easy to find what is equal the maximal tangential stress is equal 77.2 minus sigma 1 minus sigma 3. The two main stresses just the difference divided by 2, 52.2 megapascal. And we can define that the angular inclination of the side of the segment of the mechanical body and the action of the flat stress state inclined to the direction pi divided by 4, so it is 45 degrees, to the direction of the main stresses, to direction of the application of the main stresses to the sides of the segment of mechanical system, which inclined by the angle at which the tangential stresses parallel to the sides of the inclined segment of mechanical system will be equal to 0. That's the main sides, the main directions, the main stresses, sigma 1, sigma 3, sigma 2 directed to the direction parallel and opposite to the axis x, perpendicular to the plane of the consideration. And this is angle of inclination 45 degrees of the side of the application of the maximal tangential stresses. So we have the main stresses, and we have the angle of inclination of the main directions and the main sides. So next can be find the main deformations of the elastic element. Yes, we can, but we just only have the formulas as very simple, got in the article, as I remember, 7.3 as well. So when we substitute the magnitudes of the stresses, and we as well assume that sigma 2 is a stress in the direction of the abscissa axis directed towards the perpendicular to the plane of the considered shore or the considered exercise. That is why the sigma 2 is equal to 0. We assume as one of the assumptions of the plane stress state. So, but this is in the intermediate magnitude between 77.2 and minus 27.2. This in accordance to the magnitudes of sigma 1 and sigma 3, considering the sign as well. This is Poisson ratio 0.20h. This is modulus of the elasticity for the stretching compression. And we have finally that the deformation in the first direction, my direction is equal 4.059 by 10 power to minus 4. Yes, and this is deformation, and so which is dimensionless deformation. The dimensionless because we have the megapascal of the dimension of the sigma of the stresses and the megapascal, that's the dimension of the molar elasticity. So we have just dimensionless deformation. This is specific characteristics per each depends on the absolute magnitude of the deformation, depends on the watch size the deformation specific applied. So greater will be the absolute deformation. In the second direction, the deformation equal to minus 667, minus 0.667 by 10 power minus 4, and the deformation negative, yeah, with a minus sign. And as well, we have it is in the direction perpendicular to the plane of the consideration of flat stress state of the assigned exercise. And the deformation in the third method main direction is equal minus 2.325 multiplied by 10 power minus 4. Okay, and what is the deformation of the elastic element, the volume change? What is volume change? We have the formula of that is volume change equal to the total of three linear deformations. Linear is mean deformations in directions of the main stresses. So we have together that the volume deformation theta is equal to 1.04h multiplied 10 power minus 4. That's okay. Next question is, what is the specific potential energy of the deformation of the elastic element? We have the formula got in the previous one, as I remember, maybe 7.5 article, this article of the total energy of the deformation, specific potential energy of deformation. So per unit of the volume of the, besides per unit of the volume, and attributed to definite one point, because in the material of the mechanical body, this can vary. So when we substitute all magnitudes, so here we have the two elastic modulus. See, we have 0 second one, second one stress in direction of the in the direction perpendicular to the plane of the considering of the flat issue. Besides, we have 0 magnitude 1 to 2 times. So we have 0 2 summations in the bracket. So we have only we have only minus 27 point. We have only the 2 mu. Yeah, the total of zeros. After that, we had that it is 187.5 power 10 minus 4 millijoule by cubic millimeter. Millijoule by this dimension. Joule is a unit of the energy of the work in the physics, but it is millijoule, 1,000 parts of joule. Yes, per cubic millimeter. Specific potential energy to change the volume of the elastic element equals. So first, let's consider which one part of this one magnitude got of the specific potential energy of deformation of the elastic element is spent for change of volume elastic element. We had this formula got in the one of the previous, maybe 7.5 article, and this is this factor not dependent on the stresses. And in the stresses, we have only 3 stresses squared. So after the substitute, we can have that it is 8.7 multiplied 10 power minus 4 millijoule per cubic millimeter. We compare these two energies, this energy, specific energy, potential energy of the deformation of the segment of the mechanical body. This is the energy spent for change of the volume. This is just only part energy of the deformation. This is much less, so it is 8.7 that we have 187.5. So this, so we understand that the greatest part of the energies spent not for the change of the volume, the segment of the mechanical body, but spent on the change of the shape of the mechanical segment of the mechanical body. And what is the energy due to the formula got in the article? 7.5. As I remember, we have this is a formula after the substitute of the magnitudes. Here we substituted the ratio of Poisson. This is modulus of elasticity. 3 came from the formula of finding of the energy, specific energy potential spent for change of the shape. After the substitute, we can find that it is 178.8 multiplied 10 power minus 4 millijoule per cubic millimeter. That is all energies. And it's easy to understand that if we have these two energies, the energy spent for change of the volume, energy spent to change the shape of the segment of the mechanical body, we can consider this together. We will have the total specific energy spent for the deformation of the segment of the mechanical body. And let's consider the verification of the strength of the elastic element. First, let's consider the concepts. The hypothesis of the destroy the mechanical element. We considered, as I remember, 4 concepts. Excuse me. The potential energy we consider, as I remember, in the article 7.4, excuse me, not 7.5, but in the article 7.5, we consider the concepts of the destroy of the elastic element, and we said that actually we have many concepts, maybe few tens concepts of the strengths of the segment of the mechanical body, but we had considered only 4 concepts, more usual 4 concepts. The first one is the simplest, that is the concept of the maximal normal stresses. So we assume that the equivalent stress equal to maximal normal stresses. Maximal we have in the first direction 77.2, and this is less than permissible normal stress assigned in the exercise 100 megapascal. This due to the concept of the hypothesis. We will say a hypothesis, not concept of hypothesis of the maximal normal stresses. The check of strength is done. Yes, so we have 77.2 less than 100 permissible stress. The verification of strength according to the hypothesis of largest axial deformations. Due to largest axial deformation, which one deformation is actual? Let's consider here. Okay. So deformation 4. Just to the magnitudes with not a sign. 4.0, 4.039, etc. Okay, the first one is the maximal deformation 77. So let's consider what we have in the brackets here. What we have in the brackets here. Well, this what we have in the brackets, and we have the equivalent normal stress. It have to be equal. The brackets magnitude, this is 84.16. This is less than assigned permissible magnitude of the normal stresses, 100 megapascal. Okay. The next verification of the strength according to the hypothesis of the maximal tangential stresses. Equivalent stress have to be equal for the difference of the biggest and the lowest in the sequence of the main normal stresses. 77 minus, the lowest minus 27, the minus by minus is plus, and so we have 104.4. Oh, this is more than the permissible level of the normal stresses allowed 100 megapascal. So check the strength of the segment by the hypothesis of the maximal tangential stresses is not enough strong segment. And let's consider, just for the example, the verification strength according to the hypothesis of the highest specific potential energy of the shape change. Yes, we consider by the formula got in the previous article, square root of the difference is the last one. Difference very look like the equivalent stress. by the hypothesis of the maximal tangential stresses. Yeah, sigma 1 minus sigma 3, here we have sigma 3 minus sigma 1, but you have squared. So the squared magnitude is positive. Anyway, after the substitute, we got that the sigma equal to 93.8. This is less than the assigned magnitude maximal 100, 100 megapascal. So the check of the strength by the hypothesis of the height specific potential energy of shape change is done. That's why of 4 hypotheses we did consider, the only one was not fulfilled. The strength is not satisfactory. Okay, questions and comments. 761, the sequence of determining the main deformation, specific potential energy of deformations, and checking the strength of the elastic element at a given volumetric stress state. Yeah, we did use the formulas we got previously. So formulas covered the assigned magnitudes of the normal and tangential of the normal tangential stresses, normal applied in two opposite direction for the flat stress state, as we consider that the axes usually of ordinata y and the applicata z, and we assume that as well is the third direction, but the fourth is the first one, is a longitudinal direction in the usual considerations. That is the direction of the stresses in the parallel to the abscissa axis. But for the flat stress test, we consider the exercise, the abscissa axis is perpendicular to the plane of the consideration of the flattish shore. So first we have to determine usually the angle of the inclination, but the formula, as you remember, is a tangent of double angle of the inclination equal to 2 towers divided by difference of 2 sigmas, etc. After that we find the magnitude of the main stresses as the total divided by 2 of 2 assigned stresses plus 1 divided by 2 multiplied by square root of the mathematical equations dependent on the tangential stresses, etc. We have the main stresses as well. We assume that we had the one more stress for the flat stress state equal to 0 in the direction perpendicular to the plane of the consideration of the flattish shore. And besides, we define the main tangential stress as a difference of the first and the third mean normal stresses. Yes, that is divided by 2. This is the main tangential stress. Specific potential energy. We have the formula. This specific potential energy we can find general for the deformation of the segment of the mechanical body onto the stress state. But as well, we have the formulas of determining the energies, specific potential energy spent for the change of the volume of the segment of mechanical body and the stress state, and energy spent for change of the shape of the mechanical body together. They have to be equal together. I mean the specific energies to change the volume and the energy to change the shape of the segment mechanical body together have to be equal to the general energy spent for the deformation of the segment of mechanical body, etc. That's why we have to use the formulas got previously. 763, checking the strength of elastic element at a given three-dimensional stress state according to the following criteria: the highest normal stresses. We just have to take the maximal of the main stresses as the highest normal stress to compare with as equivalent one, the highest normal stress main sigma 1, and compare to the assigned to the permissible magnitude of the normal stress. Another hypothesis, maximum axial deformation as a function of the main stresses and the Poisson's ratio. When we found by the formula, so the deformations, epsilons, so we can find the maximal of the deformations, and finding this maximal deformation, one of 3 in the main directions of the application of the main normal stresses. And in the brackets in the formula, finding the maximal deformation. In the brackets, we can find the equivalent normal stress to compare with the permissible level of stress. This would be the check by the hypothesis of the maximal axial deformations. The next key hypothesis, the tangential stresses, highest tangential stresses. This is it's very simple, but a little bit very reliable, very simple calculation hypothesis. Just we can find the difference of two main stresses, sigma 1 and sigma 3. This will be almost equivalent to the maximal tangential stress. All those tangential stress to find, we have to the difference of the main stresses divide by 2, so sigma 1 minus sigma 3 divided by 2. But for finding of the equivalent stress to compare with the normal stress permissible, we can just only consider the numerator, sigma 1 minus sigma 3, which will be the equivalent normal stress by the hypothesis of tangential stresses. This is the hardest hypothesis. So if you do the segment of the mechanical system on the mechanical body itself under the stress state satisfies the hypothesis of tangential stresses, maximal tangential stresses, perhaps this is just enough, and you have be sure that all other hypotheses will be fulfilled. The check will be fulfilled by the other hypotheses. Although we have the assignment, to find the to check the strength of the segment of the mechanical body by the criterion of the highest specific potential energy of deformation. So we have a little bit complex formula. As a part of it, we have under the root one of the summands, which corresponds to the check by the maximum tangential stress is about the same. But we have to find the square root of just a half multiplied by brackets. In the brackets, we have 3 summands, and each of summand is corresponds to a definite magnitude of the tangential stress, but in the definite planes of the application. And so actually this characterizes the energy of the deformation, specific potential energy of deformation. Thank you.